Hello dear students, today we are learning this derivation, electric field of a dipole. This is case 1, electric field of a dipole at any point on the axis of dipole. So let's consider a dipole like this, PQ minus Q plus Q, right? The distance between the charges is 2L and we are taking at any point A on the axis of dipole. It doesn't really matter whether you take the point on this side or that side. The derivation remains same, right? So in this case I have taken point A on this side. Okay. So O is the center of the dipole, the midpoint on the axis. Okay. So distance of this point A from this point O is R. Okay. So what will happen to AP? This distance A to P, this will be distance R plus this much, that is distance L, half of 2L. So this will be R plus L, R plus L. Similarly, AQ would be R minus L. You can imagine yourself. Now we will find the electric field due to charge minus Q at point A. Electric field due to a point charge at any point is equal to Q by R square, where R is the distance. So in this case this will be KQ by R plus L whole square. Now since this is a negative charge, the direction of electric field would be towards the charge, that is EP. This is as shown. Similarly, if you write the electric field EQ, it will be same KQ, but distance would be R minus L whole square and it will be away from Q. You can see here EQ. This is the distance R minus L, okay, and this is a positive charge, it will be away from the charge. So EP and EQ you have figured out. Now the electric field of dipole is what? Is just collection of two charges. So the net electric field at A would be a vector sum of these two fields EP and EQ, and we can see EP and EQ are anti-parallel to each other. So the net sum would be the difference, right? So EQ minus EP would be the net electric field. So let's just do EQ minus EP because EQ is bigger, right? Ultimately it will be away from Q. You can see EQ minus EP. Why EQ is bigger? Because charges are same. This point is closer to point Q. So EQ would be higher in value. So EQ minus EP. So now from this point onwards, the net electric field EQ minus EP, and we will solve that mathematically to get to the final derivation. Plug in the values of EQ and EP from what we have figured out, like this. Take KQ common, this will be this, right? Then take the LCM, R minus L whole square, R plus L whole square. So this will be the numerator. This is something you have to see for yourself. There is nothing like physics here. This is pure basic maths. KQ, this is A square minus B square. So A plus B, A minus B. And below here it is R minus L, R plus L, so it will become R square minus L square, A square minus B square, and since there is a square of each, so it will be R square minus L square whole square. Now electric field would be KQ. Here L and L will go, it will become 2R and 2L. You can see yourself. R square minus L square whole square remains as is. Now if R is very greater than L, which is typically the case because in dipole the charges are separated by a very small distance, and we are talking about a point which is considerably far from the dipole as compared to the length L. So this point R will be very greater than L. So R square minus L square can be considered near about same as R square, right? So now this entire thing will become KQ 4RL upon R to the power 4, because this becomes R square, so R square plus square R to the power 4. Now this will be, now we'll plug in the value of K also, 1 upon 4 pi epsilon naught. If the charges are kept in vacuum, K will be 1 upon 4 pi epsilon naught. 4, I write 2 as 2 into 2, so 2 times 2ql, 1 r kills this r to the power 4 and this becomes rq. Now coming here, 2ql is nothing but your dipole moment p, so E will become 1 upon 4 pi epsilon naught 2 times p upon r cube, 2 times p upon r cube. Right. In the vector form, I can write electric field will be in the same direction as dipole moment. This is one important point. Right. The direction of electric field will be same as the direction of dipole moment. Now this happens irrespective of the orientation of the point, whether you take the point on this side or on this side. The net electric field will always be in the direction of dipole moment. So if the point was here, somewhere here, let's say point B, so even then the direction of electric field would be in the direction of dipole moment. See, dipole moment ka direction is like this here, right? So in both the cases, the net electric field would be in the direction of the dipole moment, right? So your formula that you should remember for your numericals, E is equal to 1 upon 4 pi epsilon naught 2p by r cube. Thank you. Hello dear students, so this is our next derivation, electric field of dipole. This is case 2 when point is on the equatorial plane. What is equatorial plane? So consider this is the dipole, the two charges kept at P and Q, minus Qn plus Q. So if you draw a line perpendicular as a perpendicular bisector of this axis line PQ, right? And imagine a plane passing through this line perpendicular like this. This is a equatorial plane like this. Okay. So the point is A, where we are willing to calculate the net electric field of this dipole. The approach would be same, that we will calculate the electric field of this point charge and this point charge at this place, do a vector sum, right? So this distance is total 2L, so this is L, this is L. The point is at a distance R from the center of the dipole, right? Always remember in the numericals, the formula has to be applied in a way that the distance has to be considered from the center of the dipole. This is R. Now this is R, this is L, that means this hypotenuse would AP or AQ would be square root of R square plus L square, very simple. Now this angle is theta, this angle is also theta, right? If this is theta because alternate interiors. If this is theta because of the corresponding angles, right? Now first understand the electric field of this charge minus Q. It will be along the line joining this point and this towards the charge. Because of a negative charge, the electric field is always towards the charge. So like this white color EP. Similarly, plus Q will be along the line joining the point and this charge, but it will be away from the charge because of a positive charge. The electric field is always away from the charge. Now, these are the two vectors now, EQ and EP, whose resultant you are interested in. So normally now this problem has shifted from electrostat problem to a vector problem. You have two vectors oriented like this and you are supposed to find out the resultant. It's not that difficult. We'll use the componentization technique. Let's imagine one horizontal or x-axis or a y-axis like this. Take x-axis and y-axis, or you can say horizontal and vertical. Let's try to resolve these two electric fields EQ and EP along these two lines. If you focus on EQ is like this. So its one component would be EQ sine theta and one component would be EQ cos theta. Similarly, EP One component will be downwards EP sin theta, other component would be EP cos theta, right? And EQ sin theta and EP sin theta, they are opposite to each other, right? And EQ and cos theta and EP cos theta, they are in the same direction, so they will add up. Okay, now this is regarding the direction and orientation of the electric field. Now let's just put the values also in place. You anyways understood this part. Dipole center is O, right? And the distance O is R, so OP and OQ is equal to L. AP and AQ both will be this, right? Now EP, that means the electric field of this point charge, minus Q. This will be KQ by R square. So R is what? Distance between the point charge and the point. So this is R square plus L square, square root ka square. So this will be KQ by R square plus L square. Similarly, you can see the same value would be there for EQ also. In terms of value, there will be no difference. Same value. K is 1 upon 4 pi epsilon naught. We are considering the charges are kept in vacuum. Okay, now we have to just add these two values EP and EQ, but vectorially, right? These are not numbers, they are vectors. So what we will do is, since EP and EQ are equal in magnitude, their EQ sin theta and EP sin theta being opposite to each other, they'll cancel out each other. So your net electric field would be just along this horizontal line, and it will be EP cos theta plus EQ cos theta. So that's what we are writing here. So net electric field would be EP cos theta plus EQ cos theta. Now EP is KQ by R square cos theta, EQ is KQ by R square cos theta. Both the values are exactly same. It will be 2 KQ cos theta upon, this is x plus x 2x, right? Now this 2 KQ cos theta we will replace by a value L upon square root of R square plus L square. You can check it for yourself. In this triangle, if you find out cos theta, the cos theta would be base upon hypotenuse. Base is L upon hypotenuse, which is R square plus L square square. So I plugged in the value of cos theta, rest everything is same. You can see here. So this will become as K times, now 2QL is dipole moment, we know that. So P ho gaya wo. So K into P upon this will be R square plus L square power 3 by 2. This is simple maths. Now again same assumption. The point is very far, right, the dipole. So R will be very greater than L. So this R square plus L square will be approximated to just R square. So this will be KP R square. Now L square is ignored. It's just R square to the power 3 by 2. Now square and by 2 will cancel out each other. So we'll just have P upon R cube. 1 upon 4 pi epsilon naught is the value of K. So electric field would be E is equal to 1 upon 4 pi epsilon naught P by R cube. Right. Now in terms of vectors, this will be written as E is equal to 1 upon 4 pi epsilon naught minus P by R cube. Notice I have put a minus sign. Now let's understand why this minus sign is there. What is the direction of dipole moment in this case? Dipole moment is always in the direction, is along the axis, but from the minus charge to the plus charge. So if I consider the direction of dipole moment for this dipole, it will be towards the positive side of x-axis. And see where the electric field is coming, it is right opposite to the dipole moment direction. And this will happen irrespective whether the point is on this side or this side, right? You can try for yourself. In all the cases, electric field would be always opposite to the dipole moment. That's the reason in the vector form we have put minus. So there are two differences. If you compare this case with the case 1, where the point was on the axis of the dipole, there first of all the formula had a 2p upon r cube. So we can say on the axis of the dipole the electric field is twice as that of the equatorial plane. On the axis it is twice in terms of value. If the value R is same, considering, right? So R is of course same. Now, in case of axis, the electric field was in the direction of dipole moment. But equatorial plane, it is opposite to the direction of dipole moment. Dear students, our next derivation, derivation number 3, Gauss law derivation. So under Gauss law derivation, we will have 3 derivations. This is the first one. Electric field due to a uniformly charged, infinitely long wire. Okay. So let's start with the uniformly charged wire, positively charged wire. Okay. And there's a point P. We are interested in finding out electric field due to this charge distribution. Obviously, it's not a point charge, so you cannot typically use your formula kq by r square. That is only for point charge. It can be perceived as a collection of many point charges. But if we do that approach, if we perceive this as a collection of many point charges, we'll have to do an integration. And the basic advantage of Gauss law is it avoids integration. Okay. So, few things. Let lambda be the charge per unit length. That means if the total charge is q on this wire, you divide q by the total length of the wire, you get a quantity lambda which is charge per unit length. Let P be a point at a distance r. P be a point at a distance r from the wire. Now imagine a cylindrical Gaussian surface like this, like the way I have drawn, which is passing through point P and having a length L. Okay, so radius of this cylinder would be R and the height of the cylinder would be L. Okay. Now, okay, so let's consider that we have to find net flux, net electric flux, which is coming out from this cylindrical Gaussian surface. So we'll divide this surface in 2 parts. The first part is the curved part and the other part is these 2 flat faces. Okay. Now let's first consider for the curved part. For the curved part, we can say any point which is lying on this curved part will be symmetrical with respect to the wire, right? Because it's on the curved path, all the points are at a distance r, right? So point P is symmetrical with respect to the wire, and all the points on this curved surface, they all are symmetrical. Because of this symmetry, we can say electric field at all the point will be same, uniform, right? And it will be radially outwards, Now, if you consider any small area, the electric field would be radially outwards, and the area vector we know it is always normal to the surface, so that will also be radially outwards. So considering the angle between E vector and A vector, it will be 0 throughout this surface, curved surface. So what will be the flux? Flux through the curved surface would be, let's call it phi 1. E dot A, which is EA cos 0. I told you this angle is 0. E is same everywhere, so let's take that as E. And area. Now come to the area part. When we are taking this complete curved surface area, that means we are talking about the curved surface area of this cylinder. And the formula for that is 2 pi r h. And here h is L. We are calling it L. So 2 pi r L. That is the total area of the surface. Now this is my total flux. E into area 2 pi r. So first part is done. We have figured out the flux from the curved surface. Let's come to the flat surface now. On a flat surface, you can see electric field would be like this, radially outwards, but the area vector is like this. So now this angle everywhere on the flat surface would be 90 degree. So because E, whatever value it is, maybe the E is different from this point to this point, but we are not bothered. Whatever the value would be, the area vector would be perpendicular to E, hence the net flux would be 0. On the flat surface, E and A are always perpendicular, hence flux is 0. So what is my total flux? Flat surface are giving you 0. The curved surface is giving you this much. So total flux kitna hua? Total flux is 2 pi r into E, only one on the curved surface. Now Gauss law क्या बोलते हैं? Gauss law बोलता है net flux from any enclosing surface is equal to net charge upon epsilon naught. So 2 pi r L into E. This is my net flux. What is my net charge? Now if you come to the net charge part, inside this curved surface only this much portion is there. This wire may be infinitely long, but that is all lying outside this curved surface. So if we talk about the charge inside this surface, it will be charge per unit length, which is lambda, multiplied by the length. So lambda into L, total charge. So lambda into L, net charge upon epsilon naught. Now L and L will get cancelled. E will be lambda upon 2 pi r epsilon naught. So this is your net electric field, lambda upon 2 pi epsilon naught r. Obviously it is inversely proportional to r. That means as you move away from the wire, the intensity of the electric field go down, right? In vector form, this can be written as E vector is equal to lambda upon 2 pi epsilon naught r, no change in the value, r cap vector. What is this r cap vector? It is a unit vector pointing radially outward for positively charged, radially inward for the negatively charged. So from the wire, it will be outwards for positive charge and towards the wire, inwards for negative charge, right? Okay, thank you.